All right, so 7.1 is the actual section that's in our Algebra 2 textbook. I did that 8.2 from geometry really as kind of a little prerequisite. Give you some stuff that you need to know sort of going into this. This does begin with a little recap of some of that stuff, as well as adding in a couple new functions. So trig function is actually going to be pretty similar. I can write and solve all 6 trig functions. So at this point, you know of 3 of them. You know sine, cosine, tangent. Those all do have their own inverse type functions. I guess inverse isn't really the right word here. Sorry. The reciprocal functions that you're going to learn today as well. All right. So this starts off, it says you have 2 figures here that are similar. Remember what similar means? They have the same angles, the same side ratios. So if you notice here, all these values are doubles, right? Double 4 to get 8, double 5 to 10, double 3 to 6, and so on. It says write as many ratios as you can using the 2 side lengths from triangle ABC. Write as many ratios as you can from DEF. And what do the results suggest about these? I'm not going to go through every one of these, but what I want to point out to you is that these ratios all hold true because they're similar. So like the ratio of 6 to 10 right here matches 3 to 5. Those are equivalent. If you pick any 2 corresponding sides here, they will correspond to the ones there. 8 over 6. So 8 to 6 would match 4 to 3. And obviously there's 6 different combinations you could do here, right? Because, you could do 8 to 6, you could do 6 to 8. You could do 6 to 10, 10 to 6. 8 to 10, 10 to 8. So there's 6 combinations. All 6 of these match all 6 of those perfectly. That's all this is showing you. And then this holds true for every single possible multiple of these triangles. So an infinite number of similar triangles all maintain these same exact ratios. And then that's true for every single type of triangle. Because like this has some specific angle. Well, there's some other triangle that has a different angle that still has all the same ratios as every other triangle that has that angle. That's the real value of all these trig functions. All right, so there's a symbol you're going to see today called theta. It says, so we'll start with this. 3 sides of a right triangle referred to as the hypotenuse and the 2 legs. So we talked about that. You got leg, leg, hypotenuse. They use the letter theta, which is like a 0 with like a little tilde kind of through it. You've seen it on your calculator too. It's actually the variable key right here, the 3rd thing on there. That's the theta, same thing. And it's just the symbol they use for angles pretty much from here forward. We didn't see it in the geometry textbook, but they use it here, next year's textbook, so on. And it's just used for an angle. So whenever they're talking about the missing angle, they usually use the letter theta, just because. All right, so from whatever angle you're looking at, remember you have an opposite leg, you have an adjacent leg, and then you always have your hypotenuse that's opposite the right angle. So those are the 3 parts you're always dealing with these trig ratios. Now, we said there were 6 ratios. You learned 3 last week, or last couple lessons, sine, cosine, and tangent. And you remember we had the little shortcut of Sohcahtoa as a nice way to remember these. I think of this pretty much every time I do these problems. I look at them like sine is opposite over hypotenuse, opposite hypotenuse. Cosine is adjacent over hypotenuse, right there. Tangent is opposite over adjacent, same thing. Now, each of these, sine, cosine, and tangent, has its reciprocal function, which is just the opposite ratio. So instead of doing opposite over hypotenuse, you can do hypotenuse over opposite. And the name for that, these all have weird names, that's cosecant. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. Now, you might be looking at these like, well, why did this one just get called cotangent? Why isn't this one like why isn't like sine and cosine and secant and cosecant? Because of how they're arranged, it's more about the values. Remember how we noticed that like the sine, but then we did it of a different angle, it was equal to like the cosine of the complementary angle. That's why these are more related and these are more related, and so on. But anyway, the naming's a little weird. Now, this one, you can do the same kind of thing as we did with Sohcahtoa. I do this isn't as commonly of a thing, but so CHO will be cho, SHA, sha, and CAO, cow. So cho, sha, cow is a easy way that, like when I think of these, that's how I remember what they are. Same way I remember Sohcahtoa, cho, sha, cow, and I know all 6 ratios without having to like remember a ton. I just remember 2 little weird words and I know them all. You can also just remember that, cotangent is the inverse of this one. It's adjacent over opposite, or secant is HA, and cosecant is HO. So you can remember those that way too. Whatever works for you, works for you. All right. So given any triangle, you can now write 6 complete ratios. So here's one that's already fully done. So if you're looking at angle theta here, you could do sine, and you would be opposite over hypotenuse, 21 over 29. You could do cosine, you do adjacent over hypotenuse, boom. You could do tangent, it'd be 21 over 20, boom. So those are three we've already seen. And then all their reciprocal functions are very easy. Cosecant, instead of doing 21 over 29, is 29 over 21. And secant is the reciprocal of cosine. So instead of 20 over 29, it's 29 over 20. And cotangent is adjacent over opposite, 20 over 21. So obviously these are all reciprocals of each other, and that's what those functions are. Those are not on your base plate of your calculator. There is a spot to find them. We'll get to that at another time. All right, so this problem pretty easy. Just says come up with the 6 ratios in these cases as well. So like in this case, they want you to find sine theta, cosine theta, tangent theta, as well as all their reciprocals. So cosecant theta, secant theta, and cotangent theta. Okay, so they want you to do the same thing for this triangle and for this triangle. If you want to, pause it and try it out. See if you can do all 12 of these. So this one and this one, we'll check it. All right, so there's those 6. I basically write sine and then I just flip it to write cosecant right away. And then I write cosine and I flip it to write secant. Then I write tangent and then I just flip it to write cotangent. Keeps it pretty simple. So I'll show you exactly what I'm talking about here. If I was doing this one, I said sine of theta. Sine is opposite over hypotenuse, so 12 over 37. And then I'll just jump right over and I'll go ahead and write, well, this is going to be 37 over 12. It's always the reciprocal of the sine. Here, cosine, adjacent over hypotenuse, so 35 over 37. And then flipped, the secant would be 37 over 35. Tangent, opposite over adjacent, so 12 over 35. Cotangent, 35 over 12. So basically, if you can write sine, cosine, and tangent, you can write cosecant, secant, and cotangent. All right, so hopefully feeling pretty good with those. The next piece, example 2, says knowing that tangent of theta is 15 over 8, what are the other trig ratios for theta? So this is kind of like the previous question, but instead of giving you a diagram, they give you one piece of information, which basically you want to write and draw your triangle from it. So go ahead and draw a triangle, throw a theta on there, and say, all right, if I know tangent of theta is opposite over adjacent, those are going to be 15 and 8. Now my picture is clearly not drawn to scale, but that's completely fine. I can draw my picture and make things happen. Now to do all my other ratios, because I want to do sine, cosine, tangent, we already know. Can write that one in. And then I'm also going to want to do all their reciprocals, so cosecant, secant, cotangent. I can do cotangent. That one's easy because it's just the reciprocal. It's going to be 8 over 15. But to do any of those, I need the hypotenuse. So if you remember the warm-up we did the other day, we can hit ourselves a quick Pythagorean theorem and get our missing value. So 8 squared plus 15 squared equals our c squared. Let's work that out. So 8 squared plus 15 squared, and go ahead and root that. We get 17. So we can figure this value out using good old Pythagorean theorem. Don't forget about that guy. All right, so now that we know that, we can crank these out, right? So the sine of theta, opposite over hypotenuse, 15 over 17. Cosecant is just the reciprocal of that. Okay, cosine, adjacent over hypotenuse, 8 over 17. Or, flipping them, 17 over 8. And there we go. Now we're all good. So again, not really much different than the previous problem, but recognizing that you can use Pythagorean theorem to get the piece that you want. All right, take a moment, pause this one, and see if you can work this out, and we'll check. Again, I'll write all 6 out, draw my picture, see if you can get the same thing. All right, so I went and did all the prep work here. I drew my triangle with my 24 as the opposite, 25 as the hypotenuse, set up a Pythagorean theorem, and solve for that missing leg to be 7. Once I'm there, I should be pretty much golden here. So I already know sine is 24 out of 25. So cosecant is 25 out of 24. All right, so now let's actually work these. Cosine is adjacent over hypotenuse, so 7 over 25. Reciprocal, 25 over 7. Tangent would be opposite over adjacent, so 24 over 7. And cotangent, 7 over 24. And we're looking good, okay? So getting comfortable with writing all these 6 different ratios using them to create triangles, using Pythagorean Theorem, just tying a lot of trigonometry pieces together here. All right, last thing I want to look at today is this little scenario story problem deal. Finding missing length, side length. So this says a fire truck has an 84-foot ladder, as you can see here, forming a 55-degree angle. So like our theta is 55 here. The truck is 8 feet tall, so we got not labeled on here. This distance is 8 feet. So from here to here, just to the ground. The firefighter is trying to reach a window that is 75 feet above the ground. So 75 feet from here to here. Cool. Will they be able to reach the window using the ladder set at this angle? So we basically need to see, does this reach up to that building? Now, what you got to take into account is you do have an extra 8 feet. So whatever number we get from here, we can add 8 to. And we want to see, is it 75? Are they actually going to get to the window? They're going to be too high, too low, etc. So we're going to set up and solve this. So with what we have, looking at just our right triangle, we have our angle. We want the opposite, and we know the hypotenuse. So opposite hypotenuse is a sine problem. So sine 55 equals opposite over hypotenuse, x over 84. And we're going to solve this little guy out. Sine 55 is a number, right? So sine 55, double check you are in degree mode, which I am. So 0.8192 roughly equals x over 84. Put this over 1 and cross multiply. So x times 1, of course, is x. 84 times my decimal is 68.8. So I get that this is 68.8. I add my 8 additional feet from the truck, and I'm at 76.08. So feet. So the question, let's read it here and see what we think. Will they be able to reach the window using the ladder set at this angle? Kinda. They're a hair high. They're 1.8 feet high. So what could they do here? Well, this might work. You might be able to reach down and still be fine. Or you could crank this angle down 1 or 2 degrees probably and make yourself lower. You could actually figure out what you need. You could set up and solve this problem separately to do that. So in this case, will they be able to reach it? I would go with yes. I would say it's pretty much close enough. It's not perfect, but I think it's going to be able to get the job done. Could they make it perfect? Absolutely. You could change this angle to get it to be something lower, 53, 54 degrees, something like that maybe. Okay. All right, so the next one here says the sun shines at a 60-degree angle to the ground. How long is the shadow cast by a 20-foot tall flagpole? All right, so here's our flagpole. Little flag, looking good. Sun's up here shining, makes a shadow on the ground. Okay, sorry, I can't say. There we go. So we got a scenario like this. So the sun shines at a 60-degree angle to the ground. That's saying that this is 60 degrees. Okay, so because they're saying angle to the ground, the sun is shining this way. This only makes sense that this is the 60 that they're talking about. The flagpole is 20 foot tall. The question is, how long is the shadow? Real secret to these problems is reading it and creating a correct diagram. Once you're here, though, now just pick your sine, cosine, tangent and go with it. So in this case, I know the opposite and I want the adjacent. Opposite and adjacent is a tangent problem. 20 over x. Okay, tangent 60 is a number. Specifically, this number, about 1.732. Okay, put this over 1 and solve. Now, this is the one that always gives people fits when the x is in the denominator. So the quick shortcut for this is anytime your x is here, you can actually just straight up swap these values because you would multiply the x over and you would divide by the 1.7. So in my calculator, I simply will do 20 divided by that decimal, and there's my x. It's 11.55-ish. And I can get my value that way. So that's how many feet it is. That little swap move is really handy when you're solving these cross-multiplying style problems.